Welcome to Study Loop.
Okay, so we're doing chapter 18, problem 75 here. So it says sound waves in a gas can only propagate if the gas molecules collide with each other on the time scale of sound waves, period. Because that's how sound waves propagate, is through the compression and expansion of the material it's propagating through. So it says the highest possible frequency, F max, for a sound wave in a gas is approximately equal to the average collision time, the inverse of the average collision time between molecules. So this is roughly equal to the inverse collision time for molecules. And it says assume a gas composed of molecules with mass m, radius r, at a pressure T and temperature T. So we want to show what expression we can simplify the highest possible frequency F max to. So to start this out, we want to combine the ideal gas law with the mean free path to figure out what the speed is. We should know that the collision of the molecule, we gotta work backwards here. This is what we need to figure out to be able to find F max. This is given by Lm over the average speed. This is the average distance between molecules, and this is the average speed that they're going. So we just need to figure out Ln in terms of things we know, and V bar in terms of things we know. So first, we know that Ln is 1 over 4 pi root 2 r squared n over V. Now from the ideal gas law, n over V is given as P over kBt. So this is given as kBt over 4 pi root 2 r squared P. So now, what is V bar? V bar is 8 kBt over pi m. And again, these are things we know now, so we have everything in terms of things we know. So if F max is 1 over T, this is V bar over Lm, or 8 kBt over pi m times kBt over 4 pi root 2 r squared p. Awesome. So now it's just simplifying things and combining like terms here. And this comes out to being 16 p r squared root pi over m kBt. And that should be exactly what we were trying to show, and it is. Awesome. Let's move on to part B next. So part B says determine F max for 20 degrees Celsius at sea level. How many times larger is F max than the highest frequency in the human audio range? And F max human is 20 kilohertz. Okay, so F max at 20 degrees in sea level is now given by our equation. So this is 16, and P at sea level is just 1 atmosphere, so 1.013 times 10 to the 5 pascals. And our R, in this case, we can use the normal molecule for air radius, and we've used that in the past, is 1.5 angstroms. And we have to square this, and times the square root of pi, and the molar mass of air is 29 atomic units. Convert that to kilograms per unit, and times 1.38 times 10 to the negative 23 joules per Kelvin, and lastly 20 degrees Celsius is 293 Kelvin. Awesome. Let's plug all that in. this comes out to being 4 times 10 to the 9 hertz. So that means sound waves can only propagate through air up to 4 gigahertz. So how many times larger than the human or the highest human frequency is this? Well, F max over F max human equals 4 times 10 to the 9 over 20 times 10 to the 3. And this comes out to being 2.3 times 10 to the 5 times larger. So sound waves can have much higher frequencies than humans can hear, which we already know it can go higher a little bit because dogs can hear things that we can't at higher frequencies than we can, for example.